So please help welcome Wayne and Guillaume. They're going to talk about Kubernetes and Docker. Thank you.
Thank you, sir. Thanks. Is my mic on? Yeah, it's on. OK. So hi, I'm Guillaume Tardif. I'm the lead engineer on Docker Desktop for Mac and Windows. And with Wayne today, we're going to present the Kubernetes integration in Docker. So we'll do this in two parts. First, I'll describe the integration in the desktop side. And then Wayne will present the EE side, the Enterprise Edition side. So Kubernetes was introduced first end of last year. So we introduced it in Docker for Mac first in the 17.12 version, so that was in December. And then a couple of months later, we did the similar version on Docker for Windows. And in April, it was introduced in Docker Enterprise Edition, so following the desktop side. And all these versions pass all the Kubernetes conformance tests, so we've got fully conformant clusters. Before we dive into the details of the Kubernetes integration, a few words about Docker Desktop. So that's today the most efficient way to get started and run Docker on your development machine, Mac and Windows. You get the Docker Desktop install files, and it comes with a fully integrated virtual machine. You don't need to install VirtualBox or to configure things for the virtual machine. With that, we also take care of the networking between the host and the virtual machine. Same thing for the file sharing between host and the virtual machine. You get notifications when there is a new version coming up, so you can just install either the Edge version of Docker Desktop or the stable version. With the stable version, you get a new version every 3 months, and with the Edge version, you get a new version every month, and a bit more than that with RC versions. And this is free. You can download Docker for Mac or Docker for Windows from the store, store.docker.com. In terms of architecture, that's what it looks like with a simplified schema. So on your host, you have the hypervisor running that will run the virtual machine. Next to the hypervisor, we've got a couple of processes that will help us doing the file sharing between the host and the VM, and networking also between the host and the VM. And so on top of the hypervisor, we're running a Linux-Kit virtual machine. Linux-Kit is a Docker project that's open source, and that helps us to create virtual machine images very easily with a YAML file describing the services that run inside the VM. And all these services running inside the VM are containerized, so they are very well isolated, and they run on top of Containerd. So as part of these services, we've got the Docker engine itself that will run inside the virtual machine. And then back on the host, we have the Docker command line that you can use, and this command line will talk to the Docker engine through a socket. So that's roughly what it looks like, both in Mac and Windows. There are a few small differences, but it's really the same architecture. And just to give an example of how we do the magic of the networking, for example. So next to the hypervisor, we've got the network, a specific process to handle networking between the host and the VM. This process is called VPN Kit, and what it does is that it will automatically propagate the port exposition from the host to the VM. So say, for example, we want to start a new web container that exposes a web application on port 80. So you run your command line docker run -p 80 column 80, and this will go to the Docker engine that will start the container and expose port 80. But at this stage, port 80 is exposed only inside the virtual machine. And what VPN Kit does is that it listens to the events, receives notification when you run your docker run -p 8080, and it detects that you want to expose port 80, so it will open the port 80 on the host and then redirect all the network traffic between the host and the VM so that you can just open your browser on great. You can open your browser on localhost, and magically you will see the web application that runs inside your virtual machine without having to take care of the virtual machine IP address or these kind of things. So this was for a quick introduction on Docker for desktop, and now about the Kubernetes integration. So we wanted to have something very simple, pretty much the same thing as inside Docker desktop. We try to make things transparent, and you don't have to take care of the networking between the host and the VM, or file sharing between the host and the VM. And for Kubernetes, we try to keep things simple and transparent. So from the Docker Desktop UI, you have a single click to create your Kubernetes cluster on your machine. And then a few additional options. We will come a bit later to the other options. But the important thing is that you have just one single click to create the Kubernetes cluster. So it's a one-node cluster on your development machine. And in terms of architecture, we've added a couple of boxes on the previous diagram. So we still have the hypervisor, the Linux virtual machine, which runs Containerd, and on top of Containerd, we've got still the Docker engine. And next to the Docker engine, we have a kubelet process. And these two things, the engine and the kubelet process, will support the services above that. So you can run either swarm mode services, as you could in the basic Docker Desktop install. And next to swarm mode, you can also run Kubernetes services that will run on top of kubelet and the Docker engine. And on your host, you can use either the Docker command line or the Kubernetes command line to access the services that have been deployed. So how does it work when you hit this Enable Kubernetes button? First, we install the kube command line on your host. And then inside the virtual machine, we start creating the kube cluster. So we run kubeadm init to create the cluster. And then we start the kubelet process. We wait for kubeadm init to be finished. And then we try to detect if you are upgrading from a previous install of Docker Desktop. Say, for example, you installed Docker Desktop a couple of months ago. You had Kubernetes 1.9 running. And then you just install the latest version of Docker Desktop, which comes with 1.10. So we automatically upgrade the cluster from 1.9 to 1.10. And once this is finished, then we can populate the certificates and everything on the host so that your command line can talk to the cluster automatically. You don't have to configure certificates or these kind of things. It's done automatically. We open the kube API port on the host so that the kube command line can talk directly to the API port on the host. And you will be able to use other tools like Helm, for example, directly on your host without having to connect things to the virtual machine. And eventually we start a few controllers. We'll talk about these in just a second. So we start controllers in the kube cluster with a persistent volume claim controller and a load balance controller. So PVC, that's for persistent volumes and persistent volume claims. A persistent volume basically is the kube object that allows you to talk to the file system and to start sharing files in your kube pods. So we have this already set up in the cluster when you've installed the cluster, and you can mount either paths from your local host or paths that exist in the VM, and you can use these paths in Kubernetes pods. We have support for iNotify, so you can change files on your local host, and automatically the file events will be propagated to the virtual machine. And we have added a couple of modules in the virtual machine so that we have support for specific mounts. So you can mount NFS volumes, you can mount Git volumes, Ceph and RBD volumes as well. So that's all included in the virtual machine. You don't have anything to do for that. And in addition to persistent volume, you can create persistent volume claims. So basically that's a request to have a persistent volume set up for your pods. So we have a controller for persistent volume claims that is started with the Kubernetes cluster. And automatically, when you have a request for a persistent volume, we will create this in your host home/.docker/volumes folder. And having this in place in the cluster allows us to leverage other features such as stateful sets automatically. Just because we support persistent volume claims, stateful set will work out of the box. So this was for the file sharing part. On the networking part, We have a network setup that's integrated in our Kubernetes cluster with a simple CNI bridge. So this is all set up when you just install Kubernetes, nothing to configure in addition to the basic setup. And by default, things will be exposed inside the virtual machine, as I explained previously. And we have a VPN kit controller that will do pretty much the same thing as what we do by default on Docker Desktop. So when you start exposing a port in a pod with a load balance service, VPN kit will automatically detect that and expose the same port on your host. So let's have a look at this in practice. I'll do a quick demo of all of this. So just quickly, I can show you the UI for that. So that's Docker for Mac, and on Windows, it's pretty much the same thing. The UI is pretty much the same. So I already have enabled my Kubernetes cluster here. And I can show you quickly also, by the way, I've got a small item menu here that allows me to switch between my local Kubernetes cluster, and I can configure it to redirect things to a different cluster on Google, for example, or Amazon. So this is just a switch to use a different context. So here I'm using my cluster running on my local machine. I can use the kube command line. Check the version, for example. So I'm running 1.10.3, and I can check what I've got running on my machine or running on my cluster. So currently I've got an empty cluster. Sorry. I have installed separately Helm, so I can use the Helm tool directly on my host without any specific configuration. And I'm going to use Helm to deploy a standard Redis chart. So I'm going to deploy a Redis database on my cluster and start playing with it. So Helm init, Helm install. So I'm using the standard Redis chart. It's not a custom chart. It's really the standard one. And here, so it's installed a few things on my cluster. The chart comes with a little help here that tells me how I can connect to my cluster. So here it says you can use this command line to log into the cluster, and then once you're inside the cluster, you can use the Redis tool to connect to the database and do things with it. I can check what has been installed on the cluster. So I've got one pod for the master Redis, one pod for the slave, a few services, and the Helm chart comes with a stateful set. So it's actually using a stateful set and persistent volume and persistent volume claim because this is part of the standard Helm chart. I'm just going to check if the Redis database has been completely deployed. Yeah, so it's running. And I'm going to follow this little help here to connect to the database. So note here that at the moment, the Redis database is not exposed on my host. I've got to connect inside the cluster to be able to talk to the pod and to use the Redis CLI. So I'm going to follow this help here. This connects me inside the kube cluster. And then so here I'm using the Redis command line from the cluster. I can set one value, set foobar. Okay, save, fine. Yeah, so previously I told you this is using a stateful set and persistent volume claim. I can check on my host where this persistent volume has been created. So here I've got two objects, one persistent volume and one persistent volume claim. I can check the details of the persistent volume. And so all the data has been stored inside my home directory /.docker/volume, and it's created automatically a folder for the Redis database. And I can look at what's inside this folder. So if I yeah. Let's go inside this folder. So I've got my dump.rdb, which is the DB file for Redis, and I can look at what's inside this. And I can find my foobar value here. So it's been stored in my local folder on the host using the persistent volume and persistent volume claim mechanism. And now if I want to connect to my Redis database from the host directly, I can try this. It's not going to work now because the port has not been exposed yet on the host. So here I'm not connected. And if I want to connect, I can just change the service type of the master from cluster IP to load balanced, and automatically VPN-Kit will detect that and will expose the port on the host. So I can check which services I've got running. I've got two services here, the master and the slave service. Both of them have type cluster IP. And I can use the kube command line to change the type of the master service, for example, and change it to load balanced. So here I'm using the patch command line and changing the type value to load balancer. And I can check this has been, yeah, so now I've got the load balance service here. And I can connect to my Redis database, and everything works fine. So that's cool. We've used the kube command line. I can also use the Helm command line straight from the host without worrying about IP address of my virtual machine or these kind of things. And it would be cool as well if we could use the existing Docker Compose file that we have for existing applications and deploy a full stack of Docker Compose on my Kubernetes cluster. So we've worked on this, and we've used the extension APIs of Kubernetes. So we use the API aggregation to provide a new object inside our Kubernetes cluster. So we've got a new type of object called stack, and basically this stack object contains the same information as your Docker Compose file. So you can describe several services with mounted volumes, ports, etc. Inside the Docker Compose. And when you do a Docker stack deploy of this Compose file on a Kubernetes cluster, it will create a stack object and will create all the various services that you've specified in the Kubernetes cluster. And we can manipulate the stack objects both with the Docker command line, with, for example, Docker stack ls to list the existing stacks, and also with the kube command line, so we can do a kubectl get stacks and see the details of the stack object with the kube command line. And as previously, we automatically map the create persistent volume for the volumes that are described in the Docker Compose file, and we will automatically expose ports on the host if you specified port exposure in your Docker Compose file. So we can have a look at this. I have here a small Compose file with 3 services. So I've got a web service, an HTTP REST service words that's implemented in Java, and a database that contains specific words. And this application will create sentences out of random words. And actually, just before we use Docker Stack Deploy, in the UI here, I've shown you previously that I enable Kubernetes, and I can switch between Kubernetes and Swarm, and this will affect how the Docker Stack command works. So if I click Kubernetes, it's going to, when I run Docker Stack Deploy, it's going to deploy in Kubernetes cluster. If I click Swarm, it's going to deploy on a Swarm cluster. And I can use that with the exact same Docker Compose file to deploy the same application either on Swarm or on Kubernetes. So, sorry, Docker Stack Deploy. So I'm just deploying this Compose file, and it's going to create all these services on my Kubernetes cluster automatically and create the stack object I mentioned that will contain the definition of the various services. So this is running. I can I can see what services have been created in my cluster. Just before I do that, so here you can see that I've specified replicas 3, so I should have 3 replicas of the world service, the world service. And I still have my Redis database. I didn't shut this down, but I've got my web pod, I've got a DB pod, and I've got 3 pods for the world service. And I also have here I've got a web service and the load balance service to expose the web part on port 80. And I can see the application running. Okay. So that's my application. And basically it takes random words and creates sentences with that. So that's quite cool. I could deploy the same Docker Compose file either on Swarm or on Kubernetes, and I can check the stack object. So I can do a kubectl get stacks will list me the stacks. So I've got my demo stack that I just deployed. I can check the details of that. So basically, this contains the same information as the Docker Compose file, but in a kube object. And I can manipulate this kube object. Say, for example, I want to change the number of replicas from 3 to 8. I can use the same patch command that I used for the services previously and change the stack object to change the number of replicas. So here I'm going to use kubectl patch and change the replicas value from 3 to 8. Okay. And I can check now I've got my 8 replicas for the world service. So this is it pretty much for the Kubernetes integration on Docker desktop. And I'm going to hand over the presentation to Wayne for the enterprise part.
Thanks, Guillaume. I'll use your slides. Thank you. I'll use your slides so I can use it quickly.
Yeah. Tell me when you're ready.
Yeah, hold on.
So you can try all of this, and you can download the Docker for desktop from store.docker.com and just enable Kubernetes and start playing with this. You ready?
Mm-hmm.
Hit present.
Hi, everyone. My name is Wayne. I'm a technical lead on the UCP team at Docker. UCP is Universal Control Plane. UCP is an integral part of Docker Enterprise Edition. And today I'm going to be talking a little bit about the ways that we've integrated Kubernetes in Docker EE 2.0. Before I begin, let me just say that everything that you see here today you can try out at trial.docker.com, where we have hosted AWS trials so you can get an EE cluster up for free within minutes if you want to try any of this out. So we'll start things off with a demo. And if you saw the Docker Enterprise Edition talk a couple hours ago from my colleagues Ryan Kennedy and Anshul Pundir, you might recognize some of the features here. But we'll go a little more into detail about the technical implementation of some of these. So anyways, I'll switch over to a universal control plane install here. And if you've used Docker UCP in the past, you might recognize this UI. It's the same as we had in Docker EE 1.0, but there's a few differences. The most notable one is this new left nav pane called Kubernetes. And you can see I've already deployed a handful of Kubernetes resources in this cluster ahead of time. So we have some pods running, some load balancers, and some deployments. So you can view and manage all of your Kubernetes resources right within the UCP web UI, the same as you do with your Swarm and container resources. Let's take a look at some of the components that are running on UCP. So if we look at the containers running on a manager node, for instance, and we switch over to looking at system resources, you'll see a few containers that you might recognize already, like, for instance, the UCP controller container. This is the container that runs the web UI that you're looking at right now. But you'll also notice some new components, like the UCP Kube API server container, which runs, well, the Kubernetes API server. So this gets deployed just like any other UCP component. So we run this, we maintain it and keep it healthy, and we handle upgrading it for you when you upgrade UCP. So you don't have to do anything extra when you install Docker EE. You get a fully conformant installation of Kubernetes automatically right alongside your other components, and you don't have to do any additional management. So if we want to deploy some Kubernetes resources, we have two choices. Just like with Docker for desktop, we can use regular Kubernetes YAML files. So we can use this create button, this create Kubernetes object UI. And if we select a namespace, we'll choose default for instance, we can paste in a Kubernetes YAML file. If you've used Kubernetes in the past, you've probably seen these before. So you don't have to set up a CLI or manage credentials on your local machine. You can do everything from the browser. So we can create a pod like that. But we can also create compose files, just like Guillaume showed in his demo. So let's go ahead and do that. And I'll also show how access control works by switching over to a non-admin user. So I've switched over to an incognito tab here. And this user I've set up ahead of time has view permissions for the whole cluster, but he doesn't have permissions to create anything. So we can view Kubernetes resources. But let's try to create a compose file. So we'll go to the stacks page. We'll name this stack. And then we'll choose how we want to deploy it. So you'll notice here that we actually have three choices for how to deploy a compose file in Docker EE. Swarm services, basic containers, and Kubernetes workloads. So you can deploy the same compose file in 3 different orchestration modes. And this is really powerful because it allows you to separate out the concerns of your app definition, which is the stack file, the compose file, and the concerns of app management. In enterprise settings especially, oftentimes you'll have different people who have different concerns, like your ops team, which manages how the apps get run, versus the devs who write them. And this separation allows you to separate those concerns. So we'll choose Kubernetes workloads, and we'll choose the default namespace. And we'll use the exact same compose file that we saw in the desktop demo here. So if we paste this in, we'll try to create it, but we get an error message. And that's kind of small, but what it says is that we don't have permissions to create stacks. Our access is denied. So we can actually enforce access control within UCP for Kubernetes resources for non-admin users, just like we do for Swarm and container resources. So let's give this user permissions to create a stack. So if we switch back to the admin tab, we've created a custom role ahead of time. And this is a role just like any other role in the UCP role-based access control system. So this one's called stack create. And the operations that it has allow us to manage Kubernetes deployments, pods, services, and stacks themselves. So these are the 4 resources that we're using in this compose file. So we can grant this to our user. So we'll create a grant. This will apply to the default Kubernetes namespace. We'll select the role that we created. And the subject will be the user in question, WSUM. So if we create that grant, and we switch back to our incognito tab and try to create the stack again, this time it'll work. And we can see that we now have a pod called web running, and it also created a load balancer. So it exposed that same pod. And if we choose that load balancer, we'll see that the same app that was working on desktop works in Enterprise Edition as well. Oops. So how does this work? Our Kubernetes install integrates with UCP in 3 different places: authentication, authorization, and admission control. Authentication is basically saying, who is this request coming from, and are they a valid user of the system? Authorization is saying, okay, given that this request is coming from, say, Alice, does Alice have the permissions to make the request that she's making? And then admission control is a set of custom logic and rules which we apply to every request. And these can modify or reject requests on the fly, so we can apply UCP-specific logic to Kubernetes resources that get created. After a request makes it through these 3 phases, it then moves on to the rest of the Kubernetes system. In the case of, for instance, a pod create request, that means a pod definition will be written in etcd for the rest of the system to consume. So the first step in the request lifecycle is authentication. We use the same users and backends in our Kubernetes APIs as we do for the Swarm and container APIs. So if you're using UCP, you can use the same users and credentials in your Kubernetes resources when you're using the Kubernetes APIs as you do when you're using the Swarm APIs. And there's 2 ways to authenticate against the Kubernetes API server. The first is by supplying a client certificate in a TLS connection. If you've used UCP in the past, you've probably used client bundles. These are zip files that you can download from the UCP web UI. We generate them for each user. And included in them are certificates that UCP generates, and UCP signs these certificates with its root certificate authority. It also puts the user's username in the common name field. When the Kubernetes API server receives one of these certificates as part of a TLS handshake, it can know that it's a valid certificate by checking if it's been signed by UCP's certificate authority. And then it can figure out who it's coming from by checking the common name field. OpenID tokens work in a similar way. You can request an OpenID token from the UCP controller, and then you can use it when you're authenticating against the Kubernetes API server by including it as an HTTP header. When UCP generates an OpenID token, it signs it with a set of private keys that UCP maintains. And it also puts your user ID inside the token metadata. So when the API server gets a token, it'll say to UCP, has this token been signed by one of the appropriate keys? And if it has, then it'll pull out the user ID from the token metadata to figure out who the request is coming from. The next step is authorization. So we use the webhook authorizer in Kubernetes. And what this means is that when a request comes into Kubernetes, it makes a call back to UCP. And that call has 4 things: the user who's making the request, the noun, the verb, and the namespace of the action. So for instance, Alice wants to list pods in namespace foobar. UCP will get that call, and then it'll look up whether or not Alice has the appropriate permissions in its role-based access control system. And this is the same access control system that uses roles and grants, just like the Swarm and container resource APIs. So you can use a unified UX set of UIs and APIs to control permissions for your users across the whole set of resources. So you get a unified experience whether you're dealing with Swarm resources or Kubernetes. So this makes for a really nice experience, but it does have a limitation. If you've used Kubernetes Kubernetes YAML files online, you might have seen objects like role bindings, cluster roles, and so on. These are part of Kubernetes RBAC objects, which are used to programmatically define RBAC rules. And oftentimes they're bundled in YAML files right alongside app definitions. Today in UCP, we just ignore these objects. But in a future version of UCP, we'll automatically translate them into rules that our RBAC system can understand. So right now, instead of using those Kubernetes APIs to programmatically define access control rules, you have to do the translation manually. So here's an example of how you would do that. On the left, you can see a Kubernetes cluster role YAML definition. And then on the right is how you would make the equivalent role in the UCP web UI. The last step in the request lifecycle is admission control. These are actually custom pieces of code which we compile into the API server, which we ship with UCP. And Kubernetes has a very extensible source architecture, so it's really easy for us to add our own code to Kubernetes right before we build and ship it. As I said before, these admission controllers can modify or reject requests on the fly. And they're really powerful because they come with a lot of context. When they receive a request, they get a lot of context about that request. They know who's making it. They have the full request body and so forth. And they're also the last thing that runs in the request lifecycle. So we use these for a number of things. I'll talk about orchestrator selection and image policy signing in a second. For node RBAC specifically, the story behind this is oftentimes UCP admins will want to isolate a set of nodes so that only a particular set of users can run workloads on them. For instance, you might have your production nodes which run your production web servers or databases. And you don't want any user of the system to be able to run workloads on them because you don't want their resources to get eaten up. Maybe you only want your ops team to be able to run workloads on your production nodes. You can mark those nodes so that only certain users can access them. And the way we enforce this in Kubernetes is when a pod is being created, we have an admission controller which will make a request back to UCP saying, for instance, Bob is trying to make a pod. Which nodes does he have access to? UCP will respond with the set of nodes that Bob has access to. And then the admission controller will automatically add node selectors to that pod so that the pod will only be scheduled on those nodes. And since this is the last step in the request lifecycle, there's no way that Bob can create a pod create request to get around this. Any node selectors that he might write himself to try to schedule on the production nodes will just get overwritten by this admission controller. So we can enforce restrictions on the kinds of requests that users make with these admission controllers. Orchestrator selection works in a similar way. What's going on here is if you have Kubernetes and Swarm and you're running both types of workloads on your cluster, if they both are controlling the same set of nodes, they have a problem. They might both choose the same node at the same time to run two resource-intensive workloads on. If both of their workloads wind up on the same node, they'll fight over things like CPU, memory, and other resources. If Kubernetes and Swarm could communicate with each other, Kubernetes could say, hey, I'm about to schedule something on this node. Swarm, you should pick another node to schedule your workload on. But they can't coordinate in this way. So they can fight for resources. In this version of UCP, the way that we recommend solving this problem is by manually segregating your workloads. So you can mark certain nodes as Swarm nodes and others as Kubernetes nodes. Swarm nodes will only run Swarm workloads and vice versa. And the way we enforce this is, again, with an admission controller. We actually automatically add a Kubernetes taint to all Swarm nodes. A taint is just a label added to nodes. And Kubernetes workloads won't get scheduled on a tainted node unless they have a toleration specifically for that label. And we have an admission controller which ensures that rogue users don't add a toleration for that label. If we find it, we just remove that toleration. So again, we can use admission controllers to ensure that users only run workloads in ways that UCP admins want. The last thing we use admission controls for is image policy signing enforcement. What's going on here is Docker Content Trust is a product in Docker where users or teams can cryptographically sign images. That means that they add a signature, which is a piece of metadata, to an image. And that metadata basically acts as a seal of approval for that image's content. It says, I, Wayne, have signed this image. And I verify that it really does what it says it does and that it's not malicious. If the image content changes, the signature is no longer valid. So if you trust me, you can trust any images that I sign. You can configure UCP to only run images which have been signed by a certain set of teams or users. So you can define rules to ensure that UCP only runs trusted workloads in your cluster. In Kubernetes, we enforce this by having an admission controller where for every pod that's being created, we make a request back to UCP saying, here's all of the images and all the containers in this pod. Have they all been signed by the appropriate individuals? If they have, UCP will respond OK, and the admission controller will allow the request to go through. If they haven't, UCP will respond with an error message saying these images have not been signed, and the API server will reject the request with an appropriate error message. So in this case, we're not using admission controllers to modify requests. We're just using it as an extra layer of validation. So that's pretty much it. In summary, Docker for Desktop and Docker EE both contain fully conformant Kubernetes installations, which are totally managed for you and which come out of the box and ready to run any Kubernetes resource. EE in particular integrates with many of the enterprise-grade features we already had available for Swarm and regular containers, such as image signing, RBAC enforcement, and authentication. And again, you can try out either of these products by either grabbing the latest build of Docker for Desktop, or you can try out hosted trials of Docker EE at trial.docker.com. And now at this point, we'd love to answer any questions that you might have.
Thank you.
I don't know if you want to.
Go ahead, just really loud.
Just shout it.
All right.
Just a question about Helm. Is it provided out of the box, both for workstation and in enterprise, or is something you installed?
This is something I installed on my laptop separately from Docker for Desktop. So you can just install it and run it without any specific configuration, but it's not part of the package. When you install, the package contains the kube command line, but not Helm on desktop.
Hey guys, if you have any questions, just come up to the front. I think it looks like a lot of people are leaving and the crew's ready to go. But these guys will be able to answer questions on the side?
Yeah.
Great. Appreciate it. Thank you.
Thank you very much.